Welcome back once again to Starship Simulator for some advanced engineering procedures here on board the USS Metacomet. Today we'll be looking at a full shutdown, but first, a few items of business before we get started. These procedures that I'm doing here in these videos are completely fan-made for fun and are based only on the current demo build of the ship. They do not represent any official procedures and are subject to change in the future. Now, this is important because the ship itself will be significantly redesigned in the end product, and actually may be updated as soon as the next version of the tech demo. It seems like most of the core engineering systems will be the same or very similar, though, so these walkthroughs can potentially still be useful in the future. Consider these early videos an introduction and basic training in the shipboard systems. However, the final ship will be larger and far more complex, with additional systems and equipment. Even here in demo version 2, there is a control room, which I haven't even showcased because it remains empty for the moment. This is downstairs just outside of main engineering. But you can see how large it is and connected to 2 decks, so a significant amount of control equipment would potentially be located in here. So remember, when watching this game in its current state is a true technical demo, a proof of concept only. It's not even early access alpha, that's in the future. We're not even there yet. So don't look at this game as we see it here and think this is what it's going to be. This is an idea. You have to use your imagination and consider what it's going to turn into. However, having said all that, if you are like me and you're excited about the potential that such a game as this could bring, another week remains in the Kickstarter program. They've been smashing milestone goals over there, so if you want to contribute, you can still do that until April 19th. Look below, down in the description, for a link to that page, and the developers page if you're interested in more information. Keep in mind that the intention is for this game to be free when it's completed, so you might consider an upfront donation in lieu of a game purchase later on. Also, one of the rewards for donating a certain amount will be a full official tech manual for the entire ship. So if you're craving more of this engineering kind of thing in great detail, that might be a worthwhile prize for yourself while also helping out a small developer. Having got all that out of the way, let's get down to business here and shut down our Magellan-class starship. Here we are back down in the pit. Now, like I said, today our goal is going to be to take the ship down from fully working order back down to cold and dark. And we would maybe only do this for a couple of reasons. You would imagine some sort of full shutdown for shipyard availability, perhaps, or maybe some sort of entire computer or system reboot of the whole ship for some reason. I think for most emergency or maintenance reasons, even working on the reactor, more often we'll probably just be dropping down to battery power and maintaining battery power for around an hour or however long we need, and then bringing the reactor back up. So I think that cold and dark probably is going to be a less often scenario that we see in the eventual full game, but it's good to know for when you need it. So we're going to go through it now, and it just bookends nicely with the full startup from cold and dark, and then we'll shut all the way back down to cold and dark. And my procedure includes isolating the batteries, which prevents them from draining out, so that when you do a restart the following time, you'll actually have batteries and you can have your lights back on. You don't have to do it under emergency lighting. That's completely optional, because it is a bunch of legwork and you have to close some additional breakers, but that's up to you. So let's take a look at where we need to start here. Okay, so complete reactor shutdown to cold and dark. We begin in the cryo storage room on G deck, and so this is going to be ahead of the main evolution. This tells us that 10 minutes prior to shutdown, check shut the gas fill valves, deuterium, helium, and helium-3 refill. Shutting down with full tanks requires careful monitoring and venting, as the warming cryo gases may overpressurize the tanks. So what does that mean? Well, basically, we have a gas refill system right now that is infinite, And so at the moment, you can just leave those valves open all the time, and they will keep the cryo tanks topped off. In the real game, we're getting indications now that the refueling system is going to be much more realistic and will involve either skimming gas giants or parking up at a space station and getting loaded on board. So this step will probably not even be relevant, but you would always want to shut the valves anyways, just to ensure that they're not open on you accidentally. So those are verified shut. And here's the two heliums, helium and helium-3, and those are shut. And you can see we've got a little space in the tank here. And the thought behind this was that all of these fluids are really gases, and they're so cold. I mean, they're almost down to absolute zero. So obviously, as they heat back up after shutting down, they expand, and the pressure is going to go up. And these tanks are damageable. These can get blown out. At the moment, there's no physical or audio indications of it, but the pressure can go up to in excess of 3,000 psi. Eventually, they will explode and go down to 1 psi, or I'm sorry, 1 bar, which is 1 atmosphere pressure. My logic behind that thinking is that making sure that you've got a little bit of space in the tank and not just shutting down with the tanks completely full will help you manage that pressure a little bit better. We still will have to keep our relief loops open and let the fluid circulate through the chillers even when they're off, because this also helps regulate pressure, and so that'll prevent that. But obviously we'll get to that step later. But that is what item 1 is. The next step is vital. Item 2 is heading to our startup capacitor distributor. That's on G deck ring 1. That's the innermost ring. And we're going to verify that all of the breakers are closed there and that we are supplying power to the emergency startup system. So let's go take a look at that. That's right down the hall here. Here's the entrance to the reactor room, so then we keep going to the left, past the maintenance hatch, and here is the capacitor room. So here's the startup distributor, and everything is supplying, and we've got power going to all the feeds. Double check this, because if you have reloaded the game since you did a startup, even if you had even if you had closed all these breakers for the startup, upon reloading right now, they all open back up. So before you start taking power down, this is a vital step, because this will have reset to all open breakers. And if you're not expecting that, you may accidentally scram out your reactor when you lose power unexpectedly. So check your startup distributor capacitors. In our case, they are looking good. So now we move on to item 3, the reactor room distributor, which is on G deck on the aft bulkhead reactor room. And this is going to ensure that our capacitors are fully charged. This is the charge capacitor step. So let's go look at that. Again, another step that at the moment, because we have infinite capacitor charge at the moment, is not actually relevant, but is good practice to start thinking about now, because eventually we will have to charge these capacitors up. So here we are at the reactor room distributor, and we're just checking that all of our breakers are closed and supplying power. And then here to the start capacitors, we close that breaker, and then we would observe the feed here, the capacity charge, or I'm sorry, capacitor charge feed, and we would check for load voltage or amps. I don't know for sure, but I'm pretty sure the amps would drop to 0 once they stopped charging, as well as the live load. We'd probably still see voltage. I'm not exactly sure about that, but the main point is we're here, and we will notice that there are indications that tell us that we're no longer sending power to the capacitors, so they are charged. So at that time, we can disconnect. We want to re-disconnect so that we're not then feeding the capacitors with battery power later and draining our batteries when we don't need to. So that step's complete. Now we're getting into the real meat of it, and We're going to head over to our left to the reactor output distributor, which is on the starboard bulkhead. On each of the distribution systems, excluding the batteries, open each of the feeder breakers to each of the subsystem capacitors, weapons, shields, FTL, and sublight engines. So a review once again of the electrical system. The primary lighting and utility systems are all run off of the battery feeds. The reactor directly supplies power to the batteries and these 4 subsystems. So essentially, direct power is only going to the 4 subsystems. So we're going to start by opening up all of these supply breakers for each of the systems. So we are parked. We've gotten permission from the bridge to begin our shutdown. It's likely that people are either leaving the ship currently or already have left the ship, and it's just the engineering crew and maybe an officer of the deck somewhere, either upstairs or on the bridge, or possibly has transferred over to the hangar bay. On real Navy ships, when you pull into port and you sort of secure from sailing, the officer of the deck transfers his command station from the bridge down to the quarterdeck, which is where the gangways come on and off the ship. So a similar thing might happen here in this game, and maybe this would only be in headcanon, but for me it would be. The officer of the deck has then transferred his station to the hangar bay because that's where people are coming on and off the ship. We don't have transporters in this game. We obviously don't have gangways, although I guess if we were docked at a station we might have a physical connection, but right now most likely it would just be shuttles coming and going. So officer of the deck is there. We've gotten permission from him to shut down all of our primary systems. It's not going to affect anybody else, so here we go. We start dropping the feeds. Here's the shields, and we verify that all of these feeds and buses are de-energizing. We can also observe the lights going off down at the bottom, so it's another indication. And that is our distributor. And so the next part is just a redundancy here, but we're going to open the reactor main bus breakers to isolate the 4 primary systems. And that's just telling us it's these reactor feed breakers up here. And again, we're looking at, we look at the indications of what is downstream of whatever we're manipulating, whether that's a valve or a breaker. We identify the breaker that we're looking for, we point, we shoot, and then we observe, and we see here that the internal bus is de-energized. So that gets us with all of the main subsystems offline. And then just to finish cleaning that up, so that was 4.2 with the main bus breakers. 4.3, open the high voltage supply breakers on the reactor output distributor panel for sublight, weapons, shields, and FTL systems. So this is just further isolating all of these systems, essentially preparing for startup. Shields, FTL, not the battery distributor. We're going to keep this on for as long as possible, but all other feeds are de-energized. Observe the powering down of these systems on their associated display panels, which are these guys, and we saw they are all off. Verify the breaker for the battery system remains closed to continue charging the battery arrays as long as possible, and we just did that. Those are still going. So now, we've essentially unloaded the reactor. Once high voltage loads are removed, lower reactor power to 10%. This allows the reactor to begin gradual cooling while producing enough power to charge batteries. So 10% is going to be more than enough, at least as the electrical system is currently constituted. That may change in the future, but for right now, 10% is more than adequate to keep the batteries at full charge. So we observe, or we bring reactor power down to 10%, that's minimum, and then we observe all of our P's and T's going through the reaction chamber and through the coils over here, and there's a slight change in that we see that pressures are much closer. We're now down to that between 1 and 3 liters per second drop through the reaction chamber. And all of our temperatures are normal. Nothing is overheating or whatnot. So here we go. So now all of these fluids are looping through the reactor, removing any excess heat, bringing it back to the chillers. So this is beginning our cooldown process. And gradual cooldown is always the name of the game with reactors. Fast temperature changes inside of a reactor. That is a recipe for something called thermal shock, which can potentially lead to brittle fracture, which is the catastrophic failure of metal pieces. So of course we don't want that. So good engineering practice, we'll unload the reactor and let it start to cool on its own while we move on and do some other stuff. Now we're over to the deck distributors. This is G deck, outer bulkhead reactor room. Verify both battery aggregator breakers are closed and the bus is powered. Open the breakers to isolate any planned decks to reduce electrical load on the batteries. Warning, isolating G and F decks without switching to start capacitor power first will result in the loss of lighting and pump power to the reactor. This will result in an unplanned automatic emergency shutdown. So our deck distributors here, right? This is what it was talking about. It's talking about the battery aggregators. It wants us to verify that these two breakers are connected and currently supplying power, which it is. And this is, beyond that, this is essentially an optional step. This is telling us that if we want to disconnect any of these other decks in order to prolong battery life, let's say that we're going to shut down the battery first, do some maintenance, and then secure the system later, and we really don't need E through A deck on, we could shut these down now to reduce that battery load. I'm not going to bother with it right here because we're just going to do a full shutdown in a minute. It's also warning that if we were to disconnect these guys here for F and G deck without transferring over to the startup distributor, we could potentially have a loss of power to the critical systems and then have an unexpected shutdown, because if we just secured the decks without providing an alternative source of power, our pumps and our chillers and the reactor itself would lose power and go into scram. So that would be bad. So that's what that is telling us there. Main battery distributor, G deck, starboard bulkhead. Okay, so this is now where we are ready to really secure power. This is going to be the end of reactor supplying power, and we're going to go on to battery power on this step. So this is not super time dependent, but we are on the clock once this goes off. We'll have about an hour, between an hour and 10 minutes, depending on the electrical draw of the ship, to finish the shutdown while there's still power in the batteries. Again, if you care about that. So, on the main battery distributor, which is behind us here, when ready for reactor shutdown, isolate the battery arrays by first opening the 8 battery charge supply breakers on the main battery distributor. That is the bottom isolation breakers that are leading directly to each of the battery rooms. So these are going to the battery room inputs. So let's do that now. So we'll start disconnecting each of the battery rooms. So there we have it. So we are now, and you can see all the feeds are indicating de-energized. So we now are supplying power to the internal bus, but now it is not going anywhere. So we have now isolated all of the batteries and therefore all of the electrical systems. So we are now on battery power. We're going to open the reactor output breaker on the main battery distributor. So again, this is just continuing a down or upstream up the electrical line, opening the line for shutdown. If the battery display is no longer needed, the system may be powered down by opening the battery distributor breaker over on the reactor output panel. Warning, if shore power or emergency power is to be used, do not power down the battery display. Now this is a little bit of a leap in logic because that's not how the system works right now, but we have our reactor output, we have our external feed, which would be shore power coming from another ship or from a station, and we have our emergency solar array. Well, if the reactor is down... Oh, excuse me, sir. If the reactor is down and say we are in port and we just wanted to plug into shore, the logic behind this would be that we would connect here and then connect this to all of the batteries, right? So we would basically just be switching from one input to another. Now at the moment though, when we shut down the reactor, it de-energizes this panel, and so therefore this panel. So managing shore power, we'll have to figure that out later when those systems are more realistically in place and when we can interact with them and figure out how that actually works. But again, for now, this is just setting us up to think about that process in the future. But in this case, of course, it doesn't matter because we're not going to be using any of these. So we are going to power down that panel by opening the battery distributor breaker, which is here, the high voltage distributor. And then we saw that display has de-energized. And so now we have the reactor feed breaker is closed. We have our internal buses energized, but we're getting the no load warning, and that is expected. Open the reactor output breaker on the main battery distributor. Okay, so that's reactor output. Okay, so now we go from no load to no voltage, so the internal bus is now de-energized, and all of the systems leading from the reactor are now completely isolated with multiple steps. All the buses are de-energized, all of our panels are down. Verify the main battery distributor. Internal bus is de-energized. We just did that. We want to verify locally that battery arrays are in discharge mode. So let's go look at that real quick. Realistically, you would already have a watchstander up there, some sort of roving electrician perhaps, or if there was watchstanders stationed specifically in these battery rooms, whatever that watch station might be, we have to physically run to all of these locations to check stuff. But if you had a, say, multiplayer crew, or just thinking about it in real life, someone would be stationed here looking at these batteries already, and then would be in contact, over some sort of phone circuit, or maybe over a radio or a communicator, whatever the case may be. So you would just have whatever watchstander is over here then verify these. We have a few things to look for. To verify that they're in discharge mode, we want to make sure the feed buses are de-energized. So feed buses, good, nothing is coming in. Also here, the input bus is showing no voltage, but also no anything. No charge voltage warning on all battery cells. We see that here, no charge voltage. Observed decrease in charge levels on all batteries. So we do want to take a look at the actual charge level, which we see is down to 93.6% at the moment. We also want to take note of the time to depletion, and also take a look at the draw current and the cell condition. Just make sure that they're all healthy. Now the time to depletion is a little confusing because this is telling us that we have 21 minutes and 30 seconds. What this is not displaying is that there's actually another column to the left, which is hours. So this is actually 1 hour and 21 minutes. So when I was first writing these, and some of these had a time of depletion of like 5 minutes, I had originally said, oh, well, when you go to batteries, you've only got about 5 minutes to get stuff shut down because you're going to run out of juice. It's actually not the case. Yesterday, I finally did some full shutdown testing, and there is actually another decimal place, I guess you could say, to the left of here. It's the hours column, which we don't see here. So what this is telling us is it's 1 hour, 20 minutes, and 30 seconds. When this reaches 0, it would roll over and reset to 59 minutes. And that's what I discovered yesterday. So that's just something to keep in mind for right now. That may be changed in the future. It may just, we may be seeing like 90 to 100 minutes maybe. But if you shut down and you see this much power in the batteries, and you only see 20 minutes on time to depletion, just know that if it's this full, you have nearly an hour. In fact, you have over an hour of power left in these suckers before they go flat. So there's no need to panic. In fact, just if you're interested, with a full charge to shut down, the aft batteries went flat first at 1 hour and 8 minutes, followed by port with 1 hour and 10 minutes. The forward batteries lasted an hour and 14, and starboard lasted an entire hour and 23 minutes and 34 seconds. So whatever current draws on the starboard arrays are is apparently not as heavy as some of the other quadrants, with aft being the most. Aft for some reason has the largest pull on it. So just some numbers if you're interested in backing that up. But yes, so we're observing that we have an hour now and 18 or 19 minutes here, so plenty of time. They are still outputting, so they are in discharge mode because the output bus and the aggregator feed, those are all normal. So that's what we want to see. Yeah, note time to depletion. A full electrical load will deplete the batteries in about 1 hour and 10 minutes. We do have a warning here, though, that battery arrays will not drain at matching rates. Be sure to verify all quadrants when checking depletion levels after shutdown, and that's what I just talked about with those numbers there. You've got the different quadrants have slightly different draws on them after shutdown. So if you are keeping the batteries up for an extended time for whatever reason, don't just look at one array. Make sure you're checking all of the quadrants because they're not going to be equal. A final note on this watchstander would be required to check each of the battery arrays for proper operation. You want to make sure that there's nothing that got hung up or stuck somewhere, or de-energizing an input bus has caused some sort of problem with the battery, where who knows, maybe it's just not discharging properly, or maybe it's split open, or who knows what. Maybe there's a physical problem with the battery. So the watchstander or you if you're doing it should be required to then check each of the battery rooms. I'm not going to do that now because it's not necessary. Oh, hello. It's Admiral Cluck Norris, official mascot of the ship. I figured I should acknowledge the chicken this time because some other people apparently didn't watch the first video and were like, what the hell is this chicken? So, yeah, so we will acknowledge the Admiral there. Okay. So now we have checked our batteries. Well, let's see. We have shut down our electrical system. Nope, check that. That's too broad of a term. We have shut down our subsystems. We've unloaded the reactor, and we have disconnected the batteries from the reactor feed system, and so the electrical system now is on battery power. So we head back to the main reactor panel on G-Deck. When the battery arrays are confirmed to be in self-sufficient mode, which we just did, the reactor may be safely shut down. On the reactor panel, on the main reactor panel, place the reactor in startup mode. And we do this for a specific reason, because we have a warning here. Selecting startup rather than isolate will ensure the reactor control panel remains energized when the reactor shuts down, along with the field coils and vacuum pump. We have two options on the main controls over here. We can go to startup, we can go to isolate. Startup will close this breaker, and that is going to mean that we are supplying power from the startup capacitors, and it will open this breaker, meaning that we will disconnect from the main system completely. Now, even though we have closed everything downstream of this at this point, this will be the final failsafe. This will open this breaker, de-energize the line. If we go to isolate, it will just open both of these breakers, and while the reactor is running, it supplies its own power. The minute that we would shut it down, we would lose all power to the vacuum pump, to the field coils, to all of these indications, and I forget, it might actually just make the whole panel go blank, and so that is a dangerous condition because, as I said, we're trying to shut things down slowly and methodically in order to protect the reactor and make sure that it prolongs its life for as long as possible. So in order to prevent unexpected results, which are never good, we make sure that we put the reactor in startup mode rather than isolate. And then when we do that, we're going to verify that the breaker is opened to the reactor feed supply over here, and the output de-energizes, which is here. And then we're going to verify the reactor temperature and pump flow remains constant, and then we're going to shut it down by terminating it. We'll come back to that in a second, because we look at our various flows, pressures, and temperatures. Everything here looks correct. So we're going to put it in startup, and we're going to look for the breaker shift, which happens, and our feed, our supply here goes down to 0, confirming that the breaker is open. And so there we go. So the reactor is now running, but is now completely decoupled from anything. It's literally just self-sufficient at this point. So we will now shut it down by clicking on the terminate button, and then we verify that the reactor has indeed shut down completely by observing readings of 0 on the reaction temperature and electrical output, 10% on reaction efficiency. So basically we're looking at the reaction chamber numbers, and all the things that you would imagine are going to drop to 0 should drop to 0. Reaction efficiency will drop to 10%. We'll still have flow rate, and we'll still have pressure, and we'll still have field coil strength here at 20 Teslas. But all of these, temperature should drop to 0, output should drop. So let's do that now, and then we'll just make sure that we're going to see what we expect. So we terminate. Electrical output is 0 volts. Reaction temperature down to 0. Reaction efficiency 10%. We still have a bit of an electrical draw, but that's it. The reactor is off, and now our flows and temperatures are completely equivalent. We have equilibrium through the reaction chamber. There's no blockages. There's nothing strange happening there. Our temperatures are nice and even, so there's no like overheating at the moment. It's just cycling all of this fluid through the reactor. We essentially have a giant heat exchanger now, just a radiator, just hanging out, removing any of that excess heat from it. Once we verify that the reactor is shut down, we can stop the vacuum pump, and we will verify that the internal pressure begins rising, and we will expect an insufficient vacuum warning to cut in at greater than 10 nanopascals. We'll also de-energize the field coils, and we'll verify that the field coil strength drops to 0 Teslas. So we stop that, we look at internal pressure, and that is going up as expected. In fact, as soon as we're over 10 nanopascals, we can no longer even initiate reaction control, and we have the insufficient vacuum alarm, or indication. I guess it's red, so it would be an alarm. Yellow, what is it? Yellow is usually an indication. If you want to be real specific, it's amber. The color is never yellow, it's amber. You have amber is a warning, and red is an alarm. That's neither here nor there, I guess. Field coil's off, and we check that the strength is down to 0 Teslas, which was a unit that I was not even aware of, and a commenter pointed that out in one of the other videos, and it's basically a common metric unit regarding electromagnetic strength. So it's pretty cool. So our reactor is completely shut down. So now we're going to head to the coolant pump room, and we're going to do things in an order that makes sense to me, and I will walk you through the logic of why I've selected the things that I have chosen to power down first. So again, we would be checking any of the returning temperatures coming from the core. If there's any abnormally high temperatures, you wouldn't want to stop flow. But everything is pretty even now, so this procedure is written to turn off the pumps first and then secure the chillers. And I actually have gone back and forth on this a bunch of times while I was learning the system and while I was thinking about the system. And so The logic behind this is we stop flow first and then secure the chillers, because if we secure the chillers first and the temperature starts coming up, the fluid could start flashing back to a gas, and there would be, I think, the way I'm thinking about it logically and mechanically, as a mechanic, there would be a danger there of gas pocket forming in the impeller of the pump and causing cavitation. So as the fluid is turning into gas, now suddenly you're not pumping anything through the pump. And of course, we don't even know what kind of pumps these are, but in many pumps, in addition to the concern about cavitation that we talked about before, doing damage to the impeller itself, many pumps also use the fluid that it's pumping as a coolant. Rather than risk having a gas through there, this procedure has us securing pumps first, then doing the chillers. So hopefully that all makes sense and explains why we're doing it this way rather than another way. At the moment, there is no penalty for shutting everything down in actually any order, as far as I can tell. But with these procedures here, we will start with the pump. So in fact, we will start with the deuterium pump, which is over on our right. Okay, so we see that it's operating totally fine and normal, as expected. So we're going to shut the discharge valve first, then we will secure the pump. Then we'll observe that flow rate will drop. Now we're going to leave the inlet open for pressure relief. And again, we don't know exactly what kind of valves these might be. Are they globe valves? Are they butterfly valves? Are they gate valves? Many types of valves have an internal pressure relief built into them, so it bypasses around the seat of the valve. It equalizes pressure across so that you can just shut it and not have to worry about overpressurizing your pipe. But as I was talking about with the tanks themselves, once we shut down this system, specifically the chillers, temperature is going to start rising, and when temperature rises, pressure is going to rise. So keeping these valves shut, we potentially could have an overpressure situation where either the pump might overpressurize and explode, or maybe one of these pipes might split. So just thinking, again, this is just a safety concern mechanically. We are going to leave the input valves, or the inlet valves, open until all of the temperatures have come up to room temperature. So once all the pressures have stabilized, that would be a very final step after much time has passed. So let's just take a look at what it says here. So to secure the deuterium pump, we're going to shut the outlet valve, D-sup O2, which is this bad boy. We've verified that the flow rate drops to 0. Then we'll secure the pump. D-sup O1 must remain open for pressure relief until system reaches equilibrium. Once temperature has returned to shutdown levels of 235 K, shut inlet valve D-sup O1. So again, this would be much, much later. So let's do that now. So we've got flow. We're going to shut the outlet. There we go. Flow drops down to 0 liters a second. We still have 20 bar pressure. So pressure is still equalized across the pump. And then we secure it. So there we go. That's it. We only know, we would hear that the pump is off, so we would have a audio indication, and then we have the visual indication of telling us that it's offline. Next, we're going to do the same here on the helium-3 pump. So again, shut the outlet, verify flow drops to 0, secure the pump itself, de-energize it, supply, or the inlet valve must remain open for pressure relief until the tanks are back up to room temperature. So here we got 11 liters a second. We close. We observe, boom, drops to 0. And in fact, it's on both sides, so that's important. Make sure that flow rate is not moving at all, and then we de-energize the pump. All right, and then our final one will be the helium pump. We do have a small note here. Allow the helium coolant system to continue circulating until reactor chamber and helium coolant tank reach equilibrium temperature. This prevents thermal stress and possible brittle fracture of the reactor pressure vessel. Essentially just reminding us to keep circulating the coolant through the reactor as long as possible to make sure that it's going to be sufficiently cooled so when we shut it down, it doesn't start overheating on us, with no way to get that heat out of the reactor. But we should be fine here, so close the outlet, observe flow rate, drops to 0, temperature goes NA, secure the pump. Pump is now secured. So now we have no flow through the reactor. We just have our 4 tanks, which are in recirc mode right now. They're recirculating through the chillers. We verify that. We can see that we have flow just 0.1 liters a second through here and then out the other side. We have no inlet from the return line, the reactor return line. We have no flow from the refill valves. So this is what we should be observing. That's what the procedure is going to tell us now as well. So secure deuterium chiller 01. All right, so we'll start over with the D side. So here's chiller 01. Shut reactor return valve D return AO2. So we want to start isolating the return legs, not the relief legs, not the recirculation venting lines, because that would be bad. So we shut that, verify expected flow rates on the chiller inputs, then de-energize chiller 01, verify that the panel indicates offline. A gradual increase in temperature will be observed. So the expected flow rates, like I said, we expect that there should be nothing from the return line, nothing from the fill line, and we should just see some amount of recirculation through the relief or recirc line here. So it all looks good. We're now going to turn it off, and then we're going to see temperature here jump up to 30 Kelvin on the outlet. And then if we look at the tank itself, we will start seeing a gradual increase in temperature on the tank there. Now we do chiller 2, and it's all the same. Shut the return, de-energize, verify all your flows, check open the relief valve until pressure normalizes. So flows are all good. Close that first. Flows are all good. De-energize the chiller. See, temperature there is going to start very slowly going up. Right now it's essentially the same, but once you shut down, if you leave and come back after a significant amount of time, maybe 45 minutes or an hour, I came back recently and the temperatures definitely do climb back up to 293 Kelvin there, whatever room temperature is. So you will see a very gradual climb, and that's why these relief valves will stay open for the time being in order to manage that pressure so we don't blow out the tanks. Secure the helium-3 chiller. Shut the return valve, yes. Check your expected flow rates through the chiller, and then we de-energize it. A gradual increase in temperature will be observed. Check open HE3 relief 01 to vent the tank until pressure normalizes. So again, it's all the same procedure. Close the reactor return. We have no unusual flow indicators, so we de-energize the chiller. We'll notice a slight temperature increase there. We're already up to 5 Kelvin. There's 6 Kelvin, 6.5, 7. So that's already on its slow march up back to room temp. And then finally, same thing here. All of our chillers are now secured. Verify the panel is offline. And we check the vents. So obviously that was a really long step-by-step process of shutting everything down. Once you know what you're doing and you can just skim through the procedure and keep up with it really quickly, this is a super fast process. You just come in, close a bunch of valves, turn off the pumps, turn off the chillers, etc. So a reminder once again, as in the previous video, that these procedures here in the video are taking 3 to 4 times longer than they would normally take. if you were actually just doing the procedure and you were well versed in it and you understood why things were happening, it flies by. So we are now back to the main reactor panel. Verify no flow on all coolant and fuel systems. Verify no abnormally high temperatures in the reactor coolant loop or the chamber. And then we're going to select isolate over here on the reactor mode select panel. That's the right side. Verify the internal bus de-energizes. Verify main reactor panel indicates no power warning. So we see here that we have no flow, high temperature warnings, insufficient vacuum. Those are all expected. We're now going to isolate the reactor, and these are going to change from these alarms over to no power alarms. So now we have no power to the vacuum pump, none to the field coils. We still have the no flows through all here. You can see the temperatures coming up. They're still rising here in the coolant loop for the field coils. So we isolate the reactor just to open the final breaker, just to make sure it's completely electrically disconnected from everything, so it's in complete isolation. We will now go to the reactor vessel itself, and we will shut the inlet valves. And if we want, if it's desired for maintenance, we can also shut the outlet valves. So we would shut the supply. And you could stop there. I actually like to close the outlets too, just because it doesn't take any extra time. And the system is isolated elsewhere. In my mind, a big shutdown like this is in preparation for major maintenance on multiple systems. So I shut down to complete isolation and everything just to ensure a safety factor for anybody working on either electrical or fluid mechanical systems, you know? And then 11.3 here, this does give us a reminder that once the reactor plant has reached equilibrium shutdown temperature and pressures, shut the cryo pump inlet valves and the chiller pressure relief circulation valves. If pressure continues to rise in the storage tanks, the valves may remain open. Okay, so temperatures here up to 293. We can sort of imagine that maybe some time has passed and all of these systems are sort of safely back to equilibrium. We would come back, we would shut these inlets. Again, just for safety's sake, isolation's sake, it's not really necessary. You do have one valve protection on this line here, and of course you also have another valve on the reactor. I'm sure at this point we cannot shut the relief valves. If we do that, check our pressure, you can see pressure already begins to climb pretty quickly. There we're already up to 28 bar. Here comes 30 bar now. And that'll just keep going up and up and up. So remember that 1 bar is 1 atmosphere. So it's like 15, just shy of 15 psi. So there we're at 40 times atmosphere. So we're already starting to get rather high in pressure. So we reopen that. And it starts to drop back down. So that'll maintain it at 20 bar, which seems to be a normal shutdown pressure at the moment. Okay, so here we are. We are basically, if we were doing the shutdown to battery power procedure, this would basically be it. I mean, we're shut down, we're secured, systems are isolated, but the ship is still running off of the batteries for the next hour or so. We have plenty of time and juice to do what we would need to do. But of course, we are going into additional steps because we're now going to completely isolate the electrical system as well. So we start by going to our quadrant distributors, and we're going to switch the F deck distributors to startup capacitor power. So there's 4 distributors because there's 4 quadrants, and that's these guys here. So again, I know it can be a little confusing, but these are the quadrant distributors. These ones are the deck distributors. Deck distributor, and you can see because it actually is supplying all of the decks. But this is the one that we want because we want to switch from the input feed of the batteries to the input feed of the startup capacitors. So let's take a look at what the procedure has to say on that. Close the startup distributor input feed breaker. Startup distributor input feed breaker. So we will close this. We will verify that the bus remains powered and that this breaker automatically opens so that the inputs switch automatically. Observe that normal lighting switches to emergency lighting for that deck's quadrant. Repeat steps for all 4 quadrant distributors on F-deck. So let's see. So looking out the window there, out here, you can see we've got the normal lights when we switch over to the capacitors, just like when we started up. We switch. Now we've got red emergency lighting out there, but we still have power going to the internal bus and therefore to all of the supplies. So that's G-deck port. This should be, what, the forward one? Yep, here's forward. We'll do the same thing. We do a connect. Breakers switch over. We're still powered. You can see that there is now emergency lighting. That's the control room beyond there. You can see that that still has normal lighting because we have to do the upstairs, the F-deck distributors as well. So we'll get there in just a second. But we do starboard, switches over. And then over here should be aft. This would be the final one. Okay, and you can see now that because that was the 4th and final distributor that was powering regular electrical energy to the lights. What am I trying to say here? Here. There's 4 input feeds into the reactor room lighting and utilities, and it's coming from each of the 4 quadrant distributors. So as long as one is still up and running, you're still going to be getting normal lighting. So once we secure that 4th one, and not through here, but through the distributor, we lose normal lighting and we go to emergency lighting. These actually need to remain open because otherwise we would not be getting power from the startup capacitors and would de-energize everything. And so we don't want that. We need to remain on emergency power through the shutdown. But now we're back to Hunt for Red October lighting. Oh, okay, so my bad. So I read this wrong. So we should have done F-deck first, and then we do G-deck. It doesn't really matter, as long as you just make sure that you do both decks. So we start up there, over to emergency. So you see that hallway, that passageway there is now turned red. This will turn this whole passageway outside to red. Okay. And we see that things are still powered. All the buses and feeds look good. Here's F-deck aft. They make the switch. And then this should be, here's starboard, this should be the last one. Okay, so now, what have we done? We have now taken battery power off of the 2 engineering decks. If we were to go through the rest of the ship, however, we would still be getting normal lighting on E through A deck. So everything looks regular upstairs until this next step, which is where we're going to disconnect all of the deck supplies and also secure these aggregator outputs. I think. Let's just double check. So we did F deck, we did G deck, verify, observe normal lighting, switching to emergency, repeat all steps. Yes, so over to the deck distributors. Open the deck supply breakers for all decks. Open the input feed breakers for battery aggregator 1 and 2, verify that the internal bus is de-energized, and then repeat the steps for all of the deck distributors. So here we go. Disconnecting all of the decks, including F and G deck, and we can do that now because we are on the startup capacitor power. So we had that warning earlier not to do that if we were still connected to battery power, but we're fine now because we've got the alternate source. And we can go ahead and open those. Again, this is actually kind of optional. I think in the default startup, these are probably closed. But again, for completionist's sake and for complete shutdown isolation, I open those breakers as well, even though we're going to go manually do the other breakers that these would be connected to. These are the aggregator breakers that are out in the maintenance hallway. So it would go from, if you can imagine a little line diagram here, let's say you've got the battery arrays, it comes out, it goes to the aggregator, and then from the aggregator it goes to the aggregator breaker, and then from there it would come into this feed line and then go to this breaker. Excuse me, shipmate. Now, again, if you think about the electrical system as a spider web, we are shutting down all of the electrical loads, or at least closing all of the breakers from the outside of the web and then heading in. And I guess while that is there's less of a concern of overloading the system on shutdown, I do it in that order to make sure that I don't miss anything or that nothing is missed in the procedure. So that's why we're shutting down from out to in. So we'll do the decks first. We observe that they all de-energize properly, and then we take the bus down, and then that is de-energized, and we see that there's still power here. So it's like roadblocks. You know, we're putting up the roadblocks from the outer part of the city heading into the inner part of the city. But came up with that spider web analogy last time, and that really, I was really proud of that. That made a lot of sense in my head. Like, oh yeah, I wish somebody had explained it like that to me a long time ago. Probably would have made more sense. So starboard is now disconnected. No voltage. And we do verify in addition to just looking at the numbers, we do get the no voltage warning come up. Do we have one more? I think I may have hit all four. Okay, I think that's it. Yeah, because we're back to the forward quadrant here. Okay, so those are done. So like I said, our next run out here is to the battery output aggregators itself, which are in the maintenance corridor on F deck. Again, this would probably be our same roving electrician watch, or the battery room technician watch, you know, whatever that particular watch standard would be called. Here's our batteries, just taking a look at them here. You can see that, what is that, 22 minutes? We're down to about half power there. The forward arrays, if you leave the pumps and the chillers up, the forward array is what those reactor systems are attached to. So if you leave those things running for an extended time, you will drain the forward array faster than the other quadrants. So just keep that in mind. That may be why that one is a little bit lower. But here we are out in the maintenance ways. And here's our aggregators. Just a quick example here. So these are the input panels, and you can see they're de-energized because we turned them off long ago, basically after we disconnected the battery rooms from the reactor system. So these are powered down because there's no energy flowing into the batteries, only out. So again, that makes things a little less confusing because at this point, we're only looking for the panels that are on. We don't need to worry about the ones that are de-energized. We are just looking here for these suckers. And this is another step that maybe you could skip if you don't want to do all this running. It's probably not the end of the world because we have so many other breakers open. In fact, we've got those 2 aggregator breakers opened in the reactor room. So truly, you could just probably skip this step and leave this connected if you don't want to run out here, because you do have isolation back in the other room. Makes sense, right? But for returning the system back to the default shutdown state that we encounter when we first start the ship, and to have that make sense, I included the step of then securing all of these aggregator outputs. Now, I did not include disconnecting these, and we'll get to that in a minute, because we're gonna, if we want to completely isolate the arrays, we need to do that locally in the battery room. So we'll go do that after this step. But for now, we have some output aggregators to disconnect. And then we verify that the feed is off, is de-energized, no readings. Okay, so that's an input. That's an input. Here is an output because it's on. Disconnect. Disconnect. You can also observe here that there's actually like amperage drops. Put it back on. So you see here that each of the batteries has a load of 16.81 watts and 0.07 amps. So watch those numbers over there. Even if you can't read them necessarily on the YouTube, our amps drop down to 0.03 and our loads drop to 0.833. So just by shutting various breakers, we are reducing some of the what they call vampire loads. These are just electrical losses to physical connections. If you have certain appliances that are plugged in to your wall, even though that appliance is off, it's still drawing power. You're actually still feeding it electricity. That's called a vampire load. And in fact, if we don't secure the batteries locally, they will run flat because of those vampire loads. There's enough of a draw in the distribution system itself to drain them. So that's what the step is going to cover next. So here we are with port battery 01, port battery 02, and we're back to the forward battery. So there we go. So we have opened all of the deck distributor breakers here, verify that all, let's see, yeah, repeat for all 8 supply aggregators. That's supposed to be output. Just get my terminology right there a little bit. Okay, so we repeat for all 8 output aggregators, 2 battery rooms per quadrant. We just did that. Verify that all 8 input supplies are powered down. Only the output aggregators should be displaying. So that's another thing we're checking for. We want to make sure that those other panels we saw are in fact off, because there should not be any power going into the battery rooms. Now, our roving watch would have checked that on the battery consoles themselves, but that would be a second check just to ensure, you know, if you had one of those distributing panels powered on, there would be a problem somewhere. So now we go to the battery rooms F-deck, ring 2. Due to small vampire loads in the distribution system, batteries will continue to drain over time. To preserve all battery power for future startup, open battery aggregator 01 breaker for each battery array to isolate them locally. This will be 6 breakers per room, 12 per quadrant, 48 total. This step is optional, as reactor startup can be performed with flat batteries. So what that step is telling us is that for each of the arrays, we have the forward, or whatever quadrant it is, battery aggregator 01 breaker. And you can see here, so batteries are going to the output bus, going to the breaker, and then going to the aggregator itself over here, which we saw still had a bit of a load on it. And we can see here that it has a bit of a load on it. Here's our 0.03 amps that we observed on the other reading, and our 8.33 watts. But that's interesting, isn't it? Because literally everything downstream of this, from that breaker all the way up to the A deck, is secured, and yet we still have a bit of a load here. So our final step would be, and in fact, we can see that the time to depletion is still going down. So these batteries, even at full shutdown, have 34 minutes, 34 and a half minutes left on them, even though they're literally not connected to anything. So the final step here, which again is optional, is to disconnect to open this breaker. And then there we go. We now have time to depletion 0 minutes. We have no load on the output bus. It shows 240 volts, but no live load, so no wattage and no amps. So now these batteries are successfully holding their charge, and we can leave them here until we want to start up again. And for me, I like this a lot because I don't like working in the emergency lights for any longer than I have to. I like getting the ship up and running and feeling alive. I like having life breathing back through her. So I want the natural lighting, the normal lighting, to be up as soon as possible. So I like to secure these batteries. If that's something you don't want to do or don't care about, you can certainly do that. Depending on how long you're offline, these batteries will drain back to 0, and then you're essentially in the default startup state. You know, when you first load a game as cold and dark, all the batteries are flat, all of these breakers are opened, and nothing is connected. So, although if you are paying attention, I'm actually securing the electrical system a lot more than even the startup state. But again, that's just personal preference, because it's, as far as I'm concerned, if we're shutting down to this full amount, if we're going completely dark like this, then it's most likely for either mothballing the ship, like no one's going to be on for a while, or it's extended maintenance. So I like to be thorough in just shutting all these off. But anyways, we'll fast forward through this because there's 48 of these suckers, so we'll just go around the ring. We probably have a couple of people doing this, couple of shutdown guys, electricians just making the rounds, and yeah, so we'll meet back up when we have completed isolating all of the battery arrays. Okay, so we are complete with all of those, with all of that battery room stuff, and we are onto item 17, which is our final step, which is going to be the complete de-energizing of whatever remains, and that is going to the start capacitor room on G deck, opening the breaker to reactor power, and then opening all the breakers to F and G deck. The ship is now in cold and dark, shutdown, and standby mode. So that is our absolute final step. We roll into the capacitors here. We'll disconnect reactor supply. We'll disconnect F deck. And then we disconnect G deck. And there we go. All lights are out. It's pitch black. We are in full cold and dark. And this would be the absolute last step. This would be performed by the final members of the engineering watch team, right before leaving the ship. So we're going to assume that at this point we've put the ship in complete shutdown and we all have to vacate. So we're all going to head down to the planet. So we'll leave here and we're going to head to the shuttle bay and go talk to the officer of the deck, and then we should be on our way out of the ship. So here we go, onto the shuttle bay. and we'll make our way there. So clarification here. These lights are not connected to anything. These are test lights. They're not part of the electrical system, and they're not part of the real ship design. They're just on because they are temporary lighting for the technical demo. This entire area has no the electrical system has not been built back here, so these guys are just self-illuminating. So you would imagine, though, that at this point the hangar bay would maybe have some work lights, or would be illuminated by the lights of the shuttles themselves. And then we can see this planet down below that we discovered. This is not Earth. This is a random planet that I discovered. It's an Earth-like Terran type planet, about 30 minutes away, about 150 light years away from Earth, that I discovered. And apparently it is full of civilization, so it is inhabited. So we're going to get in our shuttle here and head on down there. Thank you for joining me for this for our second in the series of advanced checklists. I'll have one more, and then I'll be done. I promise. We're going to do that shutdown to battery power, and then do a startup from battery power, just because we might as well. So we'll do a dip down and then a dip back up, and I feel like that's going to be probably the procedure that we would be seeing the most underway, because it makes the most sense of what we would be doing for maintenance or damage repair reasons. So I hope you enjoyed it. Again, if you have more questions about the project overall, feel free to go visit the developers website at starshipsimulator.co.uk, I think. Something along those lines. It'll be down below. And then check out any of the other links for more info and info on the Kickstarter. Okay, that's going to wrap it up. Thank you so much once again for joining me, and I'll see you back next time for more fun with engineering systems.